Good day, everyone. Today we have a talk by Professor Kirill Kuzanyan about solar dynamo and helicity. And Professor Kuzanyan is a leading researcher at the Institute of Terrestrial Magnetism, Ionosphere and Radio Wave Propagation of Russian Academy of Science in Moscow. He got his PhD in 1995, and in 2004 he became a habilitated doctor. Since 1998, when established close research collaboration with solar physicists in China, visiting it almost every year. And now we are happy to have his presentation at our global webinar. So please go ahead. You have 45 minutes and then discussion questions. Go ahead.
Hello, everybody. Thank you, Grisha, for inviting me for this Global Reach webinar. And it's my pleasure to give it for a very broad audience in the world. I don't know how many people listen to me, so if Grisha you feel, please stop me at some point. I feel you need to ask some question. So I'm going to talk about solar dynamo mechanism and the role of magnetic helicity in this mechanism. So shall we start? I can't change the slide. Okay. So the phenomenon which we all know about, and it's a topic of the main topic of this study, observational and theoretical, is the phenomenon of sunspots and solar cyclicity. First sunspots have been detected by Galileo 1 year after he invented his telescope. And since that, it's so captivating and still insufficiently studied object. So the solar activity is a periodic change in the number of sunspots and their locations with time, and it is about 11 years. So for several recent solar cycles in 20th century, most of them were a bit shorter than that. And of course, there are examples of longer cycles, like the last cycle, 23, was very long, much more than 11 years. And there is a periodic change in the cycle magnitude, and while the magnitude of the cycle changed almost one order of magnitude between the lowest recorded and highest cycles, the period of those cycles is relatively stable. It varies up to 2 or 3 years, around 11 years. And this phenomenon of solar cyclicity, the sunspots appear first in high latitudes, in middle latitudes, then they migrate towards the equator, and then they disappear. And to understand that, it's the theory which I'm going to talk about. It's a theory of solar dynamo. And the most picturesque, the most simple way of interpretation of this dynamo solar cycle is a dynamo wave. A wave of sunspots could be plotted as a butterfly diagram on a time latitude plot, and it is a well-known phenomenon, well-known fact. And apart of sunspots, there are other manifestations of solar activity, solar cyclic activity, such as large-scale magnetic fields. Those are observed with instruments, large-scale magnetographs, for about 40 years, and they show magnetic fields all over the sun from the high latitudes to the equator. Of course, they show sunspots, but they also show large-scale background fields. Apart of sunspots, we have other manifestations of solar activity in particularly high latitudes, like polar facula. And those data has been systematized and collected by effort of several scientists, well, those in collaboration of Russian and Indian scientists. Makarov and Sivaraman published a series of polar facula data, therefore enabling the cycle not only in sunspots or mean fields, or large-scale fields, but also in polar facula. And the plan of the talk, it's a kind of a maximum plan. I would like to talk about several things in a theory, in the approach of mean field dynamo, in 2D dynamo, in direct numerical simulation, and also in the properties of the solar dynamo and helicity, the helicity conservation law, the role of anisotropic helicity, and some review of flux transport dynamo models and sunspot rising, if I have time to the end. So let's carry on. The main principle of the solar dynamo is the amplification of magnetic fields due to rotation and turbulent convection. So the solution should be periodic in time, as we have a solar cycle, and it should have form of a traveling wave. The first idea of a traveling dynamo wave was mentioned by Parker in 1955 seminal paper, and further it was elaborated in quite phenomenological models by Babcock and Layton in 1960s, and later in 1970s and 80s it has been formulated in a more rigorous way by East German school of Steinbeck, Rause, and Redler in the form of mean field dynamo. So the most toy principle, at the same, it's already an important principle of dynamo, is stretch, twist, fold. The idea of stretch, twist, fold has been formulated by Zeldovich in 1970s, but he never bothered to publish it. So it is published in this cartoon in Keith Moffat book. That we have first of all the connected magnetic line, then due to inhomogeneous rotation, it becomes stretched, and then because of inhomogeneous convection and breakage of mirror symmetry, it becomes twisted and then folded. And then we need an additional reconnection to make two loops out of one loop. And this is the main toy principle behind dynamo. So our theory should provide all these parts and our knowledge of all these parts from basic principles. The inhomogeneous rotation is differential rotation shear, which is well studied recent decades by means of heliosysmology. So we know the internal rotation of the sun, and we can learn somehow more or less qualitatively about this phenomenon. It is a lot more complicated about the other parts of this mechanism, like stretch and twist. And the idea of Parker migratory dynamo is, in modern notation, just mutual amplification of the toroidal and poloidal field due to the two factors, this alpha and the other effect called omega effect. And this provides regeneration of periodic in time and traveling in space wave. So a general
Kirill, could you briefly remind us what is alpha and what is omega dynamos? Just qualitatively.
That will be more in detail mentioned in my talk later. But we have in this cartoon we have certain parts of this mechanism. The stretch part is differential rotation, is also called omega, because omega is a rotation. And the other part is twist and fold. This part due to inhomogeneous convection, and that is called alpha because of the formalism in mean field theory. So I'll explain it a bit later why it is alpha. Okay? Can you hear me? Grisha, may I carry on?
Yes, I hear you. Okay. Anyone else?
Yeah. All right, we carry on. So these two parts in Parker migratory dynamo. And
yes, sure, go ahead. Yeah.
Oh. All right, I carry on. The basic equations for magnetohydrodynamics, which we need to solve if we want to study quantitatively the whole all processes behind solar dynamo, we need to solve all equations for magnetic hydrodynamics, such as continuity equation, equation of state, and an induction equation, momentum equation, and with all boundary conditions and all material parameters. Then in the form which it is written here, it is very simplified, and particular form of rotation or magnetic interaction to the momentum is not shown here. It is just very rough outline of the equations. And the parameters, dimensionless parameters, at which those equations can be solved and solved numerically, this parameter range varies dramatically because of the uncertainty and because it varies really a lot over the convection zone from the bottom to the surface of the sun. So in the present and in the foreseeable future, due to limited power of computations, it is not possible to resolve those equations at all scales. Therefore, we need certain simplification and certain cascade of scales and certain specification of what is actually the phenomenon we would like to understand. Direct numerical simulations provide some broad solution of those equations and provide some structures which cannot be considered as coherent. They may look like coherent, but with the change of some parameters, the structure changes. So, for example, in the simulation by Gizaro, and that is quite typical for direct numerical simulation, and several other groups have obtained similar results. There was some separation of scales, providing the difference between small scales and large scales and formation of large-scale structures. But it is very difficult to say whether this large-scale structure is a result of a certain physical process, and to what extent the parameter range of the leading parameters, the range of those parameters contribute to the formation of that scale. And if you look carefully at this diagram, you can see that it is a migration, but more likely it is not like migrating wave, just a standing wave. So it is not clear to what extent this simulation captures the physical processes, all physical processes behind Dynamo. So the idea of a mean field requires some notion of scale separation. And this scale separation is between large scales and small scales. So we are going to study some mean scale, some middle scale between the very large and very small. So what is very small scale is a kind of a background turbulent noise, the scale which is not important to us. We observe phenomena which are much larger than those scales. But the entire scale of the astrophysical body is too large for us. So we need something which varies within the scale of the entire astrophysical body. So that is going to be our mean scale. And the specific choice of this mean scale depends on what kind of data we work with and what kind of phenomena we study in the particular formulation, particular shape of Dynamo. Rigorous formulation of mean field scale is developed by the East German school of Max Steinberg, Fritz Krause, and Karl-Heinz Redler. And this work has been started about 50 years ago, and key principles were found of the scale separation in the form of and consideration of ensembles of turbulent pulsations. So that's what I said about the mean scale, which is much larger than the fluctuation scale, both in space and time, and much smaller than entire scale of the body or entire duration of the whole process, like the solar cycle. Particular values could be different, could vary, depends on what kind of the data and what kind of focus we have on particular part of the process. So mathematically, such choice of scales means we find the ensemble of turbulent pulsations, and we need to average our available data over statistically significant portions of data. Typically, the time and space are linked due to turbulent diffusivity. And this turbulent diffusivity, because the major equation, the leading equation, is of diffusion type. So then this typical ranges of this diffusivity is 10 to the 12th to 10 to the 14th centimeter square per second. And this is quite universal for lots of processes in the sun. So the differential rotation process, as I mentioned earlier, is well known due to helioseismology. But the other parts are not well studied. So let's look how mean field dynamo works. We have the induction equation, or any other equation of describing this physical process. We have the induction equation, and we plug in the ansatz of the superposition of mean and fluctuating part, such as the fluctuating part, the first correlators are zeros. But higher order correlators of the fluctuation part may not be zeros. So we put the large scale magnetic field plus fluctuating, large scale velocity plus fluctuating, and all scalar and vector quantities is decomposed in this superposition. And now we have, in consideration of this equation, the new term, and this new term is a high order correlator between large and small scales. And this is turbulent electromotive force. So, because this electromotive force can be expanded in terms of the large-scale field, this expansion, alpha and beta, they're just the coefficients for the first linear part and then the high-order derivatives. And in general, those are tensors. Tensor quantity for alpha is second rank tensor, for beta is third rank tensor. It's a correlator between the and this correlator of the two small scale quantities is described in the expansion. So that's why they called alpha, the first letter of Greek alphabet. So now we have the mean magnetic field equation for induction, for example. We have the velocity and the alpha effect. The estimate of the alpha effect has been given in the first works by Krause, is associated with the helicity of vortex flows. So it's u dot curl u in mean flow helicity. But it is not observable thing. It's very difficult to observe. So we later discuss how we can find some observation evidence of that. What is the role of the alpha and omega effects? In the simple form of decomposition with the axial symmetry, indeed the sun is, from the first glance, an axisymmetric body, and the magnetic activity is relatively axisymmetric. The non-axisymmetric part of it is relatively small. So we can have an expansion in toroidal poloidal decomposition with the toroidal and poloidal potentials of phi component of vector and magnetic field B, toroidal field, and vector potential A. And then the alpha effect provides regeneration from toroidal field to the poloidal, and also from the poloidal to the toroidal. But the most effective regeneration from poloidal to toroidal is due to differential rotation. This is the omega effect. So these two effects couple with each other, and they produce regeneration of the magnetic field. We have the dynamo equation, the mean field equation, in a thin spherical shell. The aspect ratio of this shell is thickness to the radius is relatively small. Indeed, for the whole sun, for the thick convection shell model, it is about 1/3. So 1/3 is not that small, but is relatively small. But we look for smallness of the particular turbulent processes which are much smaller than the entire convection zone. So they depend on the scale of the Reynolds number. And we introduce a dynamo number as a product of alpha and omega relative magnetic Reynolds numbers. So the Parker equations can be derived from the formal in the formal mean field equation in the approximation of the high dynamo number, high magnetic resonance number. So this is a Parker equation for 1D dynamo wave. And it's interesting to talk a bit about asymptotic solution to that. That was my earlier works about that. And we made these asymptotic solutions on the analog between Schrödinger equation and Parker dynamo equation. But in one case it is a scalar equation, in the other it's a vector equation, and it's non-self-adjoint operator in this equation. And we looked for the solution in the form of waves. Those are in quantum mechanics are probability waves or dynamo waves in our case, and energy levels, and these are the gamma, the complex growth rate, and oscillatory frequency of oscillations. The difference between in the Schrödinger and Parker equations is that because of the non-self-adjointness of the Parker equations, turning points are not, and the maximum solution is located not in the bottom of the potential well, but shifted somewhere. And we can compute and analytically solve for the leading order approximation this asymptotic solution. And in this form, we can obtain analytic solution for zeroth order and see the Parker wave in homogeneous media, in the homogeneous media of the potential well of our convection zone. So in this simple form, when we have the alpha in the form of a sine function of the simplest non-axisymmetric over the equator sine of latitude, and the simplest differential rotation is a constant multiplied with cosine of latitude because of the geometry factor, we have the wave propagating towards the equator in the most of the convection zone, and the maximum of the wave is shifted towards low latitudes, while in high latitudes there is always some part when the wave propagates to the pole. So there is some mathematical property of Parker equation which contains increase of the amplitude of the dynamo wave towards the direction of propagation and reversal of the dynamo wave to the pole, even for the homogeneous profile of the omega effect. But in reality, the situation is more complex. This is the simplest butterfly diagram based on this solution. And the situation is more complex, and if we take the real data from helioseismic inversions, real omega as a function of radius and latitude, then we can compute those more accurately under some assumption of the profile of the alpha effect. So there are two ways we can obtain from that, and in those model parameter sets we have obtained then two ways. One is a maximum 61 degree, the other is 16. Just for examples, these figures are not immediately related to the real solar conditions, just for some plausible. But the qualitatively, this solution is there are two waves, two independent traveling waves. So I would like to stress a little bit more about the importance of the polar activity for the solar dynamo, because some say that there is a kind of a seed magnetic field for the forthcoming solar cycle, and the polar branch of the dynamo wave is entirely connected with the equatorial wave, but they are in antiphase to that. And the entire theory should explain both a polar wave and equator wave. There are observations supporting this idea, and they show that there is a correlation between the current polar cycle and the forthcoming, with the shift of about half cycle, next cycle of the solar activity. There are several ways of explanation to that. But this is observational facts which were known with the schematic count of polar facula, And this is important for prediction of the solar cycle and also the understanding the mechanism of the regeneration of the dynamo. So there is some works of Makarov and Sivaraman and Makarov alone with the other co-authors in solar physics about that, about 30 years ago. So now let's consider a self-consistent model of a dynamo, because amplitude of dynamo wave varies very much from cycle to cycle, but the periodic process is more or less stable. We need to look what kind of constraints we have. First constraint that we have to get in low latitudes to get an equator-watt wave, we need to have the sign rule of the alpha and omega effects to be the product of alpha and omega should be negative in the northern hemisphere and positive in the southern. Then we obtain equator-watt wave in both hemispheres. And an important proxy of the alpha effect is helicity. So, as I mentioned in earlier Krause works, alpha effect was connected with kinetic flow helicity. But a more general way, it was formulated in Frisch-Pouquet-Lerat 1975 paper, then the alpha effect is a superposition of both magnetic part and flow part. The magnetic part is the current helicity. So then both contribute to the alpha effect with opposite sign. Then generally overall there is a balance between these two, and overall value of those helicities in physical units of the alpha effect, it's not very large compared to each of them. So there is a rough balance between these two helicities. And that enables us to use the correlation between helicities for interpretation of the alpha effect for one side. Therefore, we can say that the alpha effect can be, a proxy of the alpha effect can be the current helicity. At the same time, we can say the proxy of the alpha effect can be flow helicity, kinetic helicity. And those ideas appeared a long time ago, since Seehofer and Redler and Seehofer works on establishment of connection of current helicity and dynamo. So why helicities are so important to us? The average of magnetic helicity, the integral of magnetic helicity, A dot B, is in viscid invariant. In approximation of the infinite conductivity, this is invariant. At all scales, it is conserved. Then the cross helicity is also the integral of flow velocity and magnetic field. For no-scale separation of MHD, it is a conserved quantity. And both...
Kirill, could you tell Yote the magnetic helicity, no, just back, magnetic helicity is integral or constant at all scales, as integral or in each scale?
Oh, is integral.
Over all scales. Okay.
Over all scales, yes, yes, yes. So we can use both magnetic helicity or cross helicity as a kind of not only just because it's conserved quantity. On the one hand, we can say that what we observe in one part of the sun, or some proxy of it we can observe in one part of the sun, it represents the whole magnetic helicity in the whole convection zone. And because it is relatively slowly evolving quantity. At the same time, we can say that it is at certain scales, we can estimate large-scale mean helicity, mean magnetic helicity, with average of large-scale average of current helicity, because the current helicity is the degree of variation of changes of magnetic helicity, and that is slow compared to relaxation processes of magnetic field. And we can use magnetic helicity as a nonlinear for construction of nonlinear feedback between the generation of magnetic field and back reaction of the magnetic field to the media. So in a nonlinear dynamo is an important and dynamical quantity to organize and self-organize, self-consistent dynamo mechanism. And these ideas have been used in some of our papers, not only our papers, to construct this self-consistent model. For example, this is a Parker dynamo. And then we complement it with another equation, which schematically is shown here, some parameterized equation for helicity. It could be a magnetic helicity or current helicity or some other construct quantity, but there is an equation for revolution, a non-linear equation for revolution of that, and it is linked with A and B with magnetic fields, components of magnetic field. So, for example, in 1D model, I would like to show the equation which we actually solved for doing that. We have the equation for A, we have equation for B, and the alpha effect enters equation for A, as you can see my mouse, as a superposition of kinetic and magnetic part. And for both of them, there is a model, and for the magnetic part, for this chi c, we have an evolutionary equation, nonlinear equation. So overall, we have to solve 3 equations, and they provide certain variability of the solar cycle. And at the same time, it's a real mechanism. But one important thing that we have observations. I hope I still have time talking about that. Observations for helicity, so we can observe proxies of this helicity from real solar observations. So examples of models of with self-consistent dynamo models produce some butterfly diagram of traveling wave in magnetic field and in helicity. So that we see in the model, and we can get observational proxy of that. So in a few slides, I will talk about observational support for self-contained dynamo models. So we can observe magnetic field, sunspots, and also helicity over the sun. We have 2D models and more complicated models with also combination of magnetic and hydrodynamic parts. And for magnetic part, we have an evolutionary equation, which is in 2D case more complex. And we can associate mean magnetic helicity in this model with mean average of the observable current helicity in real active regions. So there are some examples of dynamo in our models, how we have a traveling wave, and the traveling wave in magnetic field, and also traveling wave in helicity. And these are solutions from the models. And now let's look at the observations. This is another model where we used not, here we use magnetic helicity, and in another model we use cross helicity. And the results are pretty, generally pretty similar. We have a nonlinear variability of high and low cycles. So let's look observational data. And in particular, I'm focused on long-term observations, and such data of vector magnetic fields in solar active regions have been collected from many observatories in the world, in the United States, in Japan, but most systematic data are taken for almost 30 years now, and more than 20 years have systematically been processed at Huairou Solar Observing Station in China. And the most important result of this analysis is that, butterfly diagram, I think it is some swap of the slides. Let's go carefully. What we observe in the image plane, we observe maps of vector magnetic field, the components with certain accuracy, the Bx, By, and Bz. From that, we can compute only one part of the helicity. So some assumption of local isotropy and homogeneity is necessary to associate the whole thing with what we can observe. Typical map of helicity looks like that. In the sunspot, when the strong fields are, we have the sign of helicity. But you see the current is opposite sign in leading and the following spots. But the magnetic field is also opposite, so the sign of helicity is the same. But somewhere in penumbra, the sign of helicity is opposite. So always there is a combination of positive and negative helicity. But we average data over individual statistically independent active regions, and magnetograms after some evolution can also be considered as statistically independent. And we collected the groups of statistically independent data, each more than 30 magnetograms. And for each of group, we construct in the student statistics, compute the mean values and confidence intervals. And observationally, those subsamples of data can be considered from the viewpoint of dynamo theory as an ensemble of turbulent pulsations. So they are mean quantities in the sense of dynamo theory. So what is the solution? What is the result? We have a hemispheric rule, which reflects from first point of view, it reflects north-south asymmetry in the form of Coriolis force asymmetry. And in the maximum of the solar cycle, we see a quite perfect hemispheric rule. The northern hemisphere possesses negative sign and southern hemisphere positive sign. And this hemispheric rule has been known from the first works of Norbert Seehofer on observations of current helicity in solar active regions more than 25 years ago. And let's notice that in the beginning of the solar cycle in each hemisphere and the end of solar cycle in each hemisphere, there are certain isolated time latitudinal bins, some time latitudinal ranges where the sign of helicity systematically inverses. And this is also a part of the observational helicity, and we can hope that Dynamo model can explain that. And so this is the main hemispheric sign rule, north is negative, south and positive, and this inversion is systematic. We can see that in the data from ground, in the form of for helicity and twist, and we can see data from space in some reduction of data from Hinode. We look forward for more data in the future. Oops, some slides mismatched, I'm sorry. So let's look at the observations in the model. Each model also has this, that in the beginning or end of the cycle, we see the inversion of helicity. The other models I showed earlier also show something in the beginning of each cycle, and also in the end of each cycle, there is the change of the hemispheric sign rule for helicity. So, self-consistent models of dynamo can reproduce the observational behavior of helicity, and can the helicity is not only the theoretical quantity which is necessary for construction of self-consistent model, but also an observable quantity which can be probed from observations, and the observational and theoretical model can be checked versus this observation. So that's a 1D model. We also have the change of the helicity sign in the beginning and in the end of the solar cycle, each hemisphere. So 11 years. So to the end, I would like to mention a few things. First of all, anisotropy. I mentioned that the observations only cover a part of helicity, only that part, because we compute the currents in X and Y plane. Yes?
5 minutes.
Oh, thank you. So we compute currents in XY space. So we can compute only Z component of the current. But we use the assumption of local homogeneity and isotropy. to interpret helicity. That assumption is not generally correct. And the alpha effect is generally a tensor. The helicity is also a tensor. And the assumption of isotropy requires serious consideration, because in reality there are, and that was shown in some of our works, in reality the real distribution of observable quantities doesn't agree with absolute homogeneity. There is certain departure from it, and we can estimate it in our works. Estimation the helicity as all 6 parts related to different differentiation, and we can show that this from the distribution, observational distribution of the data, that it indicates that there is no isotropy and homogeneity generally. So, and to the end, I would like to mention several words about the flux transport dynamo model, and this is a quite simple approach to physics, trying to avoid dealing with mean field quantities and scale separation, and just construct a robust machine of a dynamo just by using flux tube assumptions. And this is based on the flux tube formation from the deep inside the convection zone. This also requires some flow and of the magnetic flow from low latitudes to high latitudes by observable meridional circulation near the surface, and inobservable part of the meridional flow, yet not sufficiently observed, in the deeper part of the convection zone from high latitude to low latitudes to seed the new cycle. And this is a model of the Babcock-Layton or flux transport dynamo. It has been elaborated and studied carefully, and generally from the point of the mathematical description, the colloidal source looks very similar to the simplified homogeneous treatment of the alpha effect. Of course, we know that alpha effect is not homogeneous, and not isotropic. But in the general terms, mathematically, both models lead to similar set of equations. But from the physical point of view, it is a little bit different. So that the models of flux transport, because of their relative simplicity, have been used extensively for explanation of current solar cycle. And the problem is that indeed the structure of meridional circulation may be much more complex than it is assumed. And there are indications of multi-cell meridional circulation. So there are lots of unknown factors behind that. We don't know accurately the internal meridional circulation. We don't know accurately the buoyancy factor, why it should be that way or the other way, and flux tube formations. So I would like to mention quickly that there are also self-consistent models. They are 2D generally, which produce also double cell and multi-cell meridional circulation. Becky Yokoyama in 2017 and recent work by Valery Pipin also produces a self-consistent profile of differential rotation. But for formation of sunspots, it is a different story, which is actually beyond the core dynamo theory. It is related, but not inside the dynamo theory. An important mechanism of that is NEMP, negative effective magnetic pressure instability, which leads to formation of flux tube very near the solar surface at a few pressure scale heights. And there are observational support of that in the form of helioseismic studies, for example, Kosovich 2012, at quite shallow depth. Not in the flux tubes are seated quite shallow, not from the bottom of the convection zone. And all these complexities are somehow additional to the basic solar dynamo in order to understand the process. So I think I'm over the time. Yeah, about the model of convection, I wouldn't say. Thank you.
Thank you, Kirill. Thank you very much for this interesting and very dense talk. So we are really a compact group of people, so I propose that anyone who has a question just unmute your microphone and ask question to Kirill. Hugh, yes, go ahead.
Well, I have a simple question. It's very. Can you hear me?
Yes.
Yes, I can.
The anticipation of future sunspot activity is a very important aspect of solar physics, and the Dynamo theories exist to help predict what's going to happen. The question is there something inherently stochastic about the theoretical background in this, or is it possible simply to use existing data to predict accurately what's going to happen?
Well, it's a good question. We know that the weather is very stochastic, but still a lot of serious effort is made to predict the weather. But we know so far that we can reliably predict weather for on the range of very few days accurately. But there are methods to estimate the variability of the large scale. So the same situation is with the sun. We can see if the sunspot start formation, we can predict roughly its evolution to some extent for a few hours maybe or days, but sometimes we are wrong. Same as with the weather. But there are certainly some methods which may help you to estimate some of the solar activity, but all of them, given the general complexity of the task, are very, I would say, very inaccurate.
Okay, thank you.
More questions? I see muted microphones. Kirill, could you comment qualitatively about the relative roles of current helicity and kinetic helicity? So the Dynamo theory started from considering only kinetic helicity, and later on another component came into the game. So could you comment how this happened and what is behind it?
Okay, if you have no magnetic field, then your alpha effect, you still have alpha effect if you have a rotation in high conductivity media. But then if you have no magnetic or negligible magnetic field, then your alpha effect is connected with kinetic helicity. And that is the core, the basic idea of Fritz Krause. I try to find the slide where I put the combination of them. Yeah. So in this case, you have only one part of this equation. You see that?
Yeah.
Yeah, yeah. But as magnetic field generation grows, the other term of opposite sign also grows, and it partially compensates. Would at some point be even greater, or at some scale, because its scale averages could be greater than the flow part. And it provides some rough balance between them. But of course, there are other processes such as dissipation, ohmic dissipation, or some ejection of helicity or magnetic energy from the sun. So there is some balance between them. But one provides suppression of generation, the back reaction of the magnetic field to the media. The other provides regeneration rate. And in Fritz-Pouquet-Léonard, the alpha effect is a residual between these two. And this concept is used in our construction of self-consistent models.
So would it be more or less correct to tell that this process is self-regulating towards more or less equipartition between these two terms?
Equipartition under certain conditions, because due to different scales, conductivities, or boundary conditions, or some other particulars, it may not be equipartition, but some equipartition, yes.
Okay, thank you. Are there any more questions in the audience? You? No?
Yeah, if there's time, I would ask another question. So,
Go ahead.
about diffusivity in the interior of the sun. It's a number, or it's a scalar, or it's a vector, or a tensor. When you do theoretical work, what assumptions do you make about its variation with depth, for example, in the sun?
Well, as far as I feel now, well, generally diffusivity is not a scalar. It is generally a tensor quantity. Right. In general. But of course, for most of practical applications, usually people neglect this property and consider it a scalar. And for its value, of course, there is a molecular diffusivity. But what over the scales which we are interested about, kind of mean scales, we are interested not in molecular diffusivity. We are interested about turbulent diffusivity on certain scales. So typically there is assumption that it is there is a low diffusivity near the overshoot bottom of the convection zone, but there may be some other fine properties of diffusivity. So it depends on what kind of model you want to build. If you have a assumption of that your diffusivity is very weak, very small in some range, then you automatically change your dynamo to thin shell dynamo.
So it's more of a qualitative thing than a quantitative thing. You could still make dynamos that are different if the diffusivity is different.
Oh yeah, and it could be interface dynamo between the two layers of different diffusivities, like Parker interface dynamo. Yeah.
Right. Okay. Thanks.
You just towards once of treatment of diffusivity, I can redirect you to my textbook. I discussing a lot of different cases with isotropic and anisotropic diffusivities in different problems, but just a remark. Any other question?
I want to buy this book. Where can I buy it? Oh, Amazon. Okay, never mind.
May I ask a question?
Sure, go ahead.
Kirill, several years ago, there was a study whose author claimed that the kinetic helicity is not necessary for the alpha effect, but it helps the emergence of this effect. How do you understand this statement? Might he mean that the first term is in your equation may act alone to produce alpha effect, or he meant something else?
Well, I can't remember the study what you mentioned, so maybe I remember it in a different context. I don't know what you mean, but generally you need to have inhomogeneous turbulence, and generally you need to have a large scale departure from inhomogeneity, such as rotation and stratification. Then you can get the alpha effect. So I can't imagine that there is well, if you say there is no kinetic helicity, that means that at certain scales velocity vector and vorticity vector are correlated. I mean, no, uncorrelated. I mean, there are all occasions, and that means that it's probably no large-scale departure from symmetry, no breakage of symmetry, and maybe it is possible to construct the dynamo still with some prescribed flow, but it will not be an alpha dynamo.
So my understanding is that lack of reflection symmetry is absolutely needed for that.
Yeah, breakage of symmetry, and this is another way of calling what is the alpha effect or what is helicity, the breakage of the symmetry. Mirror symmetry. Of,
yeah, mirror symmetry. Other questions? Everyone is muted. Let me thank our speaker today, and let me thank all our participants. Next talk is scheduled in 4 weeks from now, July 8th, by Edward Conter, who will be speaking about phenomena related to ratio X-ray and flare energetics. So thank you, everyone. Goodbye. See you next time.
Thank you.
Thank you.
Thank you.
Thank you. Goodbye.
Okay.